Crunch seminar this week. So today, as usual, we have two presentations. So first presentation is a joint one presented by Professor Ricardo Vinuesa and Mr. Hamidreza Eivazi. So Dr. Ricardo Vinuesa is an associate professor at the Department of Engineering Mechanics at KTH Royal Institute of Technology in Stockholm. He received his PhD in mechanical and aerospace engineering from the IIT in Chicago. His research combines numerical simulations and data-driven methods to understand and model complex wall-bounded turbulent flows, such as the boundary layers developing around winds, obstacles, or the flow through ducted geometries. He has received the Goran Gustafsson Award for Young Researchers. And also, Mr. Hamidreza Eivazi is a visiting PhD student working with Professor Vinuesa. His research interests are in applications of deep learning for turbulent flows. So today, they will give a presentation with the title Deep Learning for Turbulent Flows and Pains Application. So let's welcome maybe Professor Vinuesa first, I guess.
Thank you very much for the introduction and for the kind invitation to this seminar. You mentioned the title, that's what we're going to be talking about today. And I want to mention that the research is funded by SERC, which is the Swedish Science Research Center, and the Goran Gustafsson Foundation, which you mentioned in the introduction. And it's going to be both Hamidreza and I that are going to be talking about the different parts of this research. So first, I wanted to give an overview of machine learning, deep learning, and probably you have seen many slides like these ones already, but just to give a short context, of course, deep learning has seen a huge success in image recognition and in many other applications, but in the context of image recognition, it has already exhibited superhuman performance. In the famous ImageNet challenges, the classification errors are around 2% with nets and 5% in the case of humans. And kind of like one of the early examples of data-driven methods is in the case of chess, where in 1997, the IBM machine Deep Blue defeated Kasparov playing chess, which turns out to be a relatively simple game for data-driven methods. It's almost possible to get good strategies by using brute force computing. And the other game that has become very popular in the recent years is Go, of course, because of the work with Alphago that I will be mentioning a bit later. And to give a bit of context, Go is significantly much more complex than chess. The complexity of a game, of a board game, can be measured in terms of the number of possible moves in one turn and the average number of turns of a typical game. And one can estimate the complexity of one of these games by taking the number of moves and raising it to the power of the number of turns. And well, if we do this operation, we can see these two numbers here. And of course, the complexity of Go is many orders of magnitude larger than that of chess. So it's not possible to bluntly compute all the possible moves, and one needs to develop some algorithms with a certain sort of intuition to come up with good strategies to play Go. And here is where the work from Google, from DeepMind comes in. Alphago was an algorithm based on artificial neural networks, which was designed to play Go, and the training was done based on the best human players. So they were observing these games, and then Alphago developed the best strategies. And here we can see a photo of Alphago playing against the world champion, Lee Sedol, and Alphago won by 4-1, which was kind of like a big accomplishment of deep learning. This happened in 2016. And 1 year after, the same team, Silver and others, developed AlphaGo Zero. And you probably also know about the particularity of this approach is that no human input was part of the training process. The algorithm played against itself, knowing only the rules of the game. And what you can see here on the right is the performance as a function of training time. And around 48 hours, a bit less than 2 days, actually at least less than 48 hours, it reached superhuman performance. So it was able to play much better than the human capability of this game of Go, and it could defeat the previous network by 100 against 0. So this kind of shows a little bit the potential of AI in a wide range of areas. Following up on this kind of introduction, we also asked ourselves the question of how AI can affect many other topics, for example, the UN Sustainable Development Goals. And we have a study published last year in Nature Communications, Vinuesa and others, where we evaluated published evidence for positive and negative impacts of AI on all these 17 goals. As you can see here, this is the team, highly multidisciplinary, with experts in AI, in engineering, in sustainability, but also in ethical, economical, and legal aspects. And we also have Max Tegmark from MIT, who was helping in the development of this work. And what we found, following up on how AI can affect very diverse areas, was that from the 169 targets that we have in all these SDGs, 79% can be positively affected by AI, whereas 35% could have a negative, could see a negative effect due to the progress of AI. And of course, although this really points out and confirms the suitability of AI to really tackle grand challenges, there is also the aspect to keep in mind that even one target being negatively affected could really destroy all the progress on the positive side, because some of these targets are really critical. So that's something to also keep in mind. If we look separately at the environment, the economy, and the society, the environment is the area with probably the largest positive impact of AI, and the economy has less positive impact. And in our study, which you can then see for more details, we see that there is not enough evidence to support the positive effects of AI on the economy. So that's maybe one of the gaps currently in the research. But we're here to talk about fluid mechanics. So after giving a bit of an overview, this is some of the recent studies, and one not so recent study on applications of deep learning to, or generally machine learning, to fluid mechanics. For instance, the early work of Milan and Koumoutsakos in 2002, where they modeled the near-world region of turbulence with neural networks. More recently, subring scale models for LES simulations. The work by Fukami and others for inflow conditions, which is actually quite relevant. Duresami and others also there in the US for RANS models. And of course, the nice work on pins, Professor Kanellakis and his group, which we are going to be discussing today with a very nice series of papers. And in this case, I highlighted the one in Science. There's also the work from Branton and others with applications to reduce order models and flow control. So there are many areas also in fluid mechanics where deep learning, or more generally machine learning, are seeing the possibility of developing improvements. And what we're going to do today is that we're going to give first an overview of deep learning applications in my group. In my group, we work with turbulence and data-driven methods machine learning. And then in the second part, Hamidreza is going to talk specifically about pins, about our work on pins, because of course that's very relevant to the audience today, and that hopefully we can get some nice input. So first of all, an overview, and in that overview, I'm going to start talking about use of recurrent neural networks for temporal predictions in the context of turbulent shear flows. And this is a work that we have already published some studies using what is a reduced order model of the near world region of turbulence. This is a model developed by Moelis and others, which basically consists of actually 9 spatial modes, and basically predicting the temporal dependencies of these spatial modes one can reconstruct the whole flow field and get a reasonable approximation to what happens in the near-world region of turbulence. Because it only contains 9 modes, it's actually quite suitable to try temporal dynamics algorithms, and we spent quite some time working on this model because of that that interesting property of being able to encapsulate the dynamics into only nine modes. And this is a visualization of the 9 time series of these modes. In this case, you can see that at some point the flow relaminarizes. We don't consider any laminar conditions, so we always truncate the time series when we exhibit, when we're observing turbulent behavior. And what you can see here is that the flow field looks similar to what one would expect in the near-world region of turbulence. So you have also the streaks, the lift-off effect, and also the span-wise movement of those streaks. So some of the most relevant features are actually there. By the way, all the results of this part of the presentation can be found in this work by Vinuesa and others in a PRF 2019. So everything is published and explained there in more detail. I'm going to talk about recurrent neural networks, and what we see here is the schematic representation of that recurrent structure in these stimulants. What I'm seeing here is the inputs, so essentially the current step and some previous steps. So I remember that I have 9 coefficients and I want to predict their temporal evolution. So I have the information of the current step and the previous ones. How many steps in the past I take, that's one input for my architecture. And then here I get the output, which would be in this current step, what is the value of those 9 coefficients for my model, essentially. And the key of recurrent nets is this part over here, this recurrent connection, which, if you think about it, what we have is that the current step, the time t, gets information from the last layer of the previous step, but also it gets information from the first layer of the previous step. These 2 arrows that we see here, they are basically giving me information from the 2 different layers on the previous, on the past. And I'm not going to go into the details of the LSTM, which is what we're going to use in this work, but basically the key is to use a gating mechanism to weight how much of the past information I need for my predictions and how much of the present information I need to have decent predictions, essentially. And that's how the training is done for the LSTM. For this problem, the problem of an equation model, we tried a number of architectures. We used this LSTM, the long short-term memory network, which is very well known because, as we know, it tackles the vanishing gradient problem for training recurrent nets. So this is a suitable architecture for these temporal predictions. And we compare our results with an MLP, with a simple MLP, where we don't embed any of the temporal dynamics in the model. And we significantly outperform the MLP, but also we get very good results. We obtain less than 1% error in the mean and 2.5% error in the fluctuations. I'm talking about the turbulence statistics. Those results can be improved even more if we consider a deeper network, of course. But also one has to be a bit careful with the length of the sequences, because if we consider too long sequences, then the results are not so good. And one needs to take into account long-term and short-term predictions kind of simultaneously. So then it gets a little bit more complicated. But this value of P, what is giving us is that we're taking information from the 10 previous steps to make the current prediction, and the results are quite good. As you can see here, the instantaneous flow field looks a lot like the reference data, and the turbulence statistics, the mean, the fluctuations, the Reynolds shear stress, and here even higher order statistics like the skewness and the flatness, or the vorticity fluctuations, they are in very good agreement. So we are able to, with this LSTM network, a very simple recurrent network model, to predict the statistics of this low-order model of turbulence. But of course, we're not only interested in the statistics, we're interested in the dynamics. And we also see, by characterizing, in this case, the Poincaré map, so we look at the correlation between the first and the third mode. This is actually the correlation between the base laminar flow and the streamwise vortices, because each of these modes is associated with a certain structure in the near wall region. And by intersecting the trajectories of these modes with the hyperplane A2 equals 0, then we get these maps, these Poincare maps. And we can actually see that they're in pretty good agreement between the reference and the LSTM model. So the dynamics are well captured. And one more aspect for the dynamics is the so-called Lyapunov exponents. So we can perturb the current trajectory of the time series, and then we can define basically the Euclidean norm of the deviation, the separation between those two trajectories. And then by looking at the initial exponential growth of the separation between those trajectories, that exponent is what is called the Lyapunov exponent, or the leading Lyapunov exponent. And basically what we can see is that by perturbing with a very small perturbation amplitude, then the Lyapunov exponent from the ODEs, from the original model, and from the LSTM, they're also in very good agreement. So once again, the chaotic nature of this reduced order model seems to be well captured by the LSTM. And another work,
Ricardo, I have a question.
Of course, go ahead.
You didn't include the laminarization, but what happens if you actually include? Can LSTM predict the laminarization?
We didn't look at that actually, and I wouldn't be sure.
Bifurcation, yeah.
I wouldn't be very confident that it can do it, but we didn't, on purpose, we didn't look at that because that would complicate the problem quite a bit. And we were interested in turbulence, but yeah, I don't know. My guess is that it's a bit tricky that it would do it.
Similarly, if you are like in the other opposite, like if you are sort of what I call young turbulence, and you go in and out of turbulence, so you have like a
like an intermittent
stationary, yeah. Did you try something like that? That's a little more ambitious.
We didn't either for one reason, and it's that this model in the end is a very simplified version of turbulence. This is not real turbulence, and we didn't think that this was going to be very. I mean, the turbulent part, the chaotic part of this system is representative of turbulence, but these intermittent turbulent, non-turbulent interfaces, we're not very sure that this is really representative of the real physics.
Yeah, you're right. Yeah.
So we didn't really go too much into that.
Do it. Yeah.
But I mean, it's of course an interesting problem. If one wants to force, to get let's say a minimum channel, and then force it to be in this. We're actually working now with minimum channels to extend this to a bit more realistic cases. And yeah, we're not going to talk about that today, but there are some promising results, but it's, yeah, I mean, it's not such a straightforward application because then you need many more modes to get something reasonable, let's say.
Because in our paper in NSF nets, in the last application,
yep.
we actually have, forward simulations of turbulence without projecting to modes. So space-time is neural network, is pins. Mm-hmm. The only input is actually the boundary conditions. So we have boundary conditions which come from DNS, then everything else is so. But there's some questions on how you can generate that actually with zero and all this. I mean, you know what I'm talking about, basically bifurcations. Yeah. Can you capture that? That's probably not possible.
Exactly. I also think that is quite challenging, but yeah, I mean, it's an open research topic. I mean, I guess to apply all of this to transitional flows, I mean, of course, it's very interesting and to see what type of transition mechanisms can be predicted. But yes, my guess is that that's challenging. But yeah, but exciting also. Thank you for the comments. And then something that I also wanted to mention is a recent study that we published also with Hamidreza in the International Journal of Heat and Fluid Flow 2021, where what we did was to use the Koopman framework, so all the work by Branton and others, all the system identification framework with a nonlinear forcing to be able to account for the nonlinearities in the system. And what Hamidreza found was that with this Koopman framework, I mean, of course, one can get much cheaper model development because you don't need to train a network, you just have this dynamical system identification, and we get similar performance and better short-term predictions. What I showed you is that the dynamics is very similar. I mean, we can really predict the dynamical quantities, but the time series diverge after a certain number of steps, and then you are in a different trajectory, but with the same dynamics. The Koopman framework is able to predict the time horizon of accurate predictions on the same trajectory is actually longer. So that's also something interesting to keep in mind. And that's also something that we're trying in minimum channels now. But that's ongoing work. Okay, and this is what has to do with temporal dynamics. One of the biggest chunks of the presentation today is going to be on convolutional neural networks. So this is also a bit related to what Professor Karniadakis was mentioning, not projected on the modes. I mean, here we're looking at the full signal, and with the application of non-intrusive sensing. So what do I mean with non-intrusive sensing? What I mean is that you have a channel like the one that you see here, and I want to be able to measure at the wall and predict what happens above the wall based on that information and some model, in this case the deep net, but there are other models as well. So we start with a DNS of an open channel flow. We do open channel, which means that at the top boundary we have a symmetry condition because the dynamics of the larger scales is simpler in an open channel than in a full channel. But there's not a big difference. And we use the Fourier-Chebyshev code Simpson from KTH. And we start with a low Reynolds number, Arita 180. I will also show results at high Reynolds number later on. And everything is explained in this paper by Wastori and others, another PhD student in my group, in the Journal of Physics conference series. So basically, what I was discussing before was a recurrent neural network, the LSTM, which is a fully connected network. And in a fully connected network, each neuron of one layer is connected to all the neurons of the next one, which means that very quickly we end up with very, very large models with very large numbers of parameters, which are tricky to train because you really have so many parameters. And when we start to work with images, and then of course, as many know, then it's better to use convolutional neural networks and convolutional layers, which are extensively used in computer vision. And the way that these convolutions work is, as you can see here, we have an input, and then we have a kernel, which is a little window of 3 by 3 or 5 by 5. And then I apply a convolution operation, which means that this point in the output, in this feature map, receives information from all these 9 points over here. Okay, so I will talk a bit more about this, but the idea is that I have a small kernel that is being sweeping all the input image, and therefore the number of parameters that we have is much lower than in fully connected networks. And then the idea here is to predict off-wall planes based on information at the plane. So use information at the blue plane that you see here, in this case, the 2 Bose shear stress components, but we could do more, and then predict the flow above the wall. So in this case, the streamwise velocity fluctuations at a certain distance above the wall. And there are different applications for this, or different motivations, but an interesting one is closed-loop reactive control. So if by measuring what happens at the wall, I can know exactly what's happening above the wall, that information can be used to produce a much more efficient control strategy, for example, with opposition control, but we are currently working on doing that with deep reinforcement learning. I will talk a bit about that later as well. So this non-intrusive sensing with deep nets is a quite promising area as well. And this is the CNN architecture and the convolutional neural network architecture that we use. We have many architectures, but this is the simpler that we have started to use actually. And in this case, you have the inputs. So we have 2 planes as an input, the 2 Bose shear stress components. The output is has only 1 plane because we're predicting only the streamwise fluctuations, and we have a total of 6 hidden layers. And in the first hidden layer, what we have is a filter that has a depth of 2, because I have 2 inputs, and the kernel has a size of 5 times 5. And the little window has 25 points now. And then this means that I have 50 parameters in the first hidden layer. This would, in a fully connected network, this would require 33,000 parameters. So, I mean, of course, for images, we want to use convolutions. And we apply this convolution operation a total of 64 times, which means that I have 64 stacked layers. And each of these feature maps or these layers, in a way, they are identifying different features on the flow. Why do I talk about features? Because these planes, this information at the wall shear stress, they have certain characteristics. They have features which can be streaks, they can be regions of recirculation, they can be strong or weak fluctuations. And all of those features are then identified by these feature maps, and therefore it's convenient to use convolutional networks to be able to exploit that information and to learn a bit more about it, essentially. The results at 180, you can see them in the other paper, but I'm going to focus, in the interest of time, in the results at Arita of 550. This is a more turbulent Reynolds number. We have a larger scale separation, and we actually start to see something with more substance. And I'm using 3 different inputs: the 2 wall shear stress components and the wall pressure. Those you can see here on the left. And the outputs, I have the 3 velocity fluctuations: string-wise, span-wise, and wall normal fluctuations at different locations, at different distances from the wall. I also consider periodic padding because these simulations are periodic. I will not talk too much about it, but if you're interested, we can discuss it. And this work is it has just been accepted in JFM. And you can see also while it comes out, all the details are in archive, so you can see all the details here. But hopefully the JFM will be available soon to discuss also all the details of the architectures. We also propose another method because everything that I was talking about before was to take the full input signal and predict the full output and the full plane. But there is another way to do it, and it's to do POD at different locations, right? And then, I mean, you can see the POD, the proper orthogonal decomposition here. So we have these spatial modes, and then we only have to predict the temporal coefficients, as we did in the first part of the presentation. And we do this in subdomains for simplicity of the evaluation of this method. We can also discuss this if you're interested. The point is that we have 2 methods. The first one is the FCN, the fully convolutional network, where we predict the whole plane, and the FCN POD, where we're predicting the temporal coefficients of the POD modes. Okay. I mean, feel free to interrupt me, or if you have anything that is not clear, just feel free to ask. So what I'm showing here are results at 2 wall normal locations. These are the string-wise velocity fluctuations. The first column is at y plus 15, which is the near wall peak, and the second column is y plus 100, which is in the outer region now, right? Because we have an Arita of 550. And the first row is the results where we are doing this prediction based on extended POD. Extended POD is basically a linear method. It's equivalent to linear stochastic estimation, and it establishes a linear relationship between the input and the output. The second row is the FCN POD, so the convolutional network with the POD modes. The third one is the DNS, so the third one is the truth. That's what we need to compare with. And the last one is the FCN, so when we are comparing and predicting the full plane. And what we can see, first of all, the extended POD, I mean, it reproduces some of the features, but it's extremely attenuated when it comes to the intensity of the fluctuations and the nonlinearities. Let's say the wiggling of those streaks is also not reproduced by the linear method. And the linear method is able to only represent the superposition mechanism, which is linear, but all the modulations, all the nonlinear parts of turbulence are not reproduced by the linear method, clearly. If we compare the DNS and the FCN, we see that the y plus 15 is nailed. I mean, it's perfect. It's very well reproduced. Farther away from the wall, of course, the correlation between the input and the output is lower, so the predictions are not so good. And in that case, the FCN POD is slightly better than the FCN. This can be maybe better observed when we look at the statistics. So I'm showing the 3 RMS values, the string-wise, span-wise, and wall normal velocity fluctuations. In orange, the FCN, in blue, the FCN POD, and in green, the extended POD, which, remember, is the linear method. And what you can see is that very close to the wall, the error in predicting the near wall region is 1%. I mean, it's extremely, extremely accurate what we can get here. Farther away from the wall, our predictions get worse. And we always outperform the linear method in all the positions. What I think is interesting is that far away from the wall, the POD-based method is better, slightly better than the FCN. And this is because for the large scales, it's probably more efficient to encapsulate the information into few spatial modes. And then we don't need to care in our network about predicting the spatial part. We only care about predicting the temporal part. So the POD is a good way, it's an efficient way of encapsulating that information for the large scales. Close to the wall, things are so small that using just an FCN to predict everything seems to be the most efficient approach. And one of my favorite parts is transfer learning. Transfer learning, we have done transfer learning in different scenarios, but today I'm going to focus on this one in the interest of time as well. And again, this is also in the JFM and in archive of Bastoni and others, so this will be soon released. What we did was we trained one network at Arita 180, okay, to do this task, this prediction task. And we wanted to we wanted to do the same task at Arita 550. So what we did was to initialize the training at 550 with the weights from 180. Okay, so we basically transfer the weights, the information that has been learned at the low Reynolds number to high Reynolds number. And what we can see here, these are results at y plus 30. What we can see here is that we can obtain the same performance or a very similar performance with 1/4 of the data set. So if we compare the network that we train for predictions at 550 with a full data set on the order of 10, 15,000 snapshots, and starting from scratch, starting from random weights. And we compare that with a network where we transfer the weights from 180 to 550, we require 1/4 of the training data to obtain the same performance. And this is, of course, excellent because the simulation at 180 is orders of magnitude cheaper than the simulation at 550. So if we can use this in a smart way, if we can do simulations at low Reynolds numbers that are cheaper, I'm talking orders of magnitude cheaper, and then reduce significantly the need of data at high Reynolds numbers, well, this is a smart way to train the networks and to use efficiently our computational resources. I see a question from Ayan. Should we take it now? Sorry.
Hello.
Yes, go ahead.
Yeah. So I just have one question. That did you use the constant learning rate, or is it a layer-specific learning rate?
The learning rate is adjusted with the Adam schedule.
Okay.
This
so
is both in the first part and in the second part.
So is it fixed throughout the layer, or it is changing?
Fixed throughout what? Can you repeat?
I am asking that is the learning rate is fixed throughout the layer, or is it changing with respect to the layer? I mean, are you using differential learning rate?
Are you talking for the different layers? That's what you mean. No, if I remember correctly, it doesn't change with the layers. It just, but it changes the learning rate with the training, of course, with a very standard Adam optimizer. But I don't think we change it for the different layers. I think it's the same, which is actually a good point. The other transfer learning, which I haven't shown here, is from layers. So what we do is that we use the first layers to learn the small scales and the last layers to learn the large scales. And then in that case, I don't think we change the learning rate actually, but it would be a good thing to do. Yeah, it would be interesting. We didn't really explore that. That other transfer learning is in the other paper, in this Journal of Physics conference series. I didn't show it today for time reasons. But yeah, I mean, that would be interesting actually to change the learning rate and see how efficient it is. I can tell you in that transfer learning, it was a similar thing, right? We were working at 180. We train a model to predict at y plus 15, where the scales are small. And then we wanted to predict at y plus 50. So we wanted to predict farther away from the wall. What we did was to freeze the weights of the 3 first layers, and we only train the 3 last layers. And of course, the last layers are looking at larger, they are identifying larger scales. And then we also reduce by a factor of 4 the training time. But I don't think that we changed the learning rate, or at least we didn't really look at it in detail. But it could be that one can reduce even more the training time. That's an interesting point. I guess that was your question, right? That was in that direction.
Yes.
Yeah,
okay, thank you.
No, thank you for the comment. That's true. I mean, unfortunately, we couldn't look at all the parameters that can be changed, but it's actually, I would point to something to keep in mind. And this transfer learning, I think it's actually one of the most promising directions also with deep learning and fluids. Okay, and then another interesting application, this is another recent work. I mean, we have been doing non-intrusive sensing, as I said. So, you use information at the wall to predict the information far away from the wall. And so far, I'm using DNS data. So I'm assuming that I know everything at the wall plane. But in reality, if you do this in an experiment, you will not have all the information at the wall. You will have some sparse measurements. And then what we want to do is that we design a GANs-based architecture, and I'm sure that many people here are familiar with GANs. We have the generative adversarial networks. So we have the generator that is trying to produce high-resolution images from the low-resolution ones using the true high-resolution pictures as a reference, right? So this is the supervised part. So the generator is becoming better at producing fake images, and the discriminator needs to identify which ones of those images are from the original data set or generated by the generator, right? And they're trained together using, well, basically game theory, and then they progressively get better at producing high resolution images. The important thing is that we are dividing our GANs architecture into two parts. The first part is to use the three inputs, and the two wall shear stress components and the wall pressure with low resolution to produce high resolution versions of those. You can see that we go from this first part to these high resolution versions of the input. And the second part is to take those high resolution inputs and produce a high resolution outputs, which are the predictions of the flow. So at the wall, I just want to increase the resolution, that's it. Away from the wall, I want to predict the flow with that highly resolved input data. To give you an idea, here on the bottom, and by the way, this is also recently published, WMS and others, and this is in physics of fluids. So if you're also interested, you can see all the details there. This architecture actually is quite interesting because we train both things together. We want to get, we are not interested in getting the best super resolution. We're interested in getting the best predictions here. So the training is designed not to, in a way, prioritize only the super resolution, but to compensate both tasks together. So this architecture is actually quite interesting because it does that. And what I'm showing here is the information at the wall. This is the instantaneous wall shear stress in the streamwise direction. The DNS is the reference. And on the first row, I am downsampling in space. So I'm downsampling in each of the two directions. This is a factor of 4 in each direction, coarser, a factor of 8 in each direction, coarser, and a factor of 16 in each direction, coarser. And this would be similar to just having a few sensors at the wall. And you can see on the second row the predictions, which in the case of 4 and 8, they are quite similar. I mean, they are quite in good agreement with reference. In the case of 16, I mean, the input barely looks like the original data. And what you can see, actually, if you compare this prediction and this DNS field, is that the fluctuations are attenuated, where I use this very, very coarse input, but the location of the extractors and their characteristics, their shape and their length, they are actually very similar. They're actually in very good agreement. And remember that my task is not to predict this in the best possible way. My task is to predict the output in the best possible way. So this step is aimed at producing something that is physical. It's not necessarily something that is fully correct. It's something that is physical. So actually with FD16, which means that we have 16 square fewer grid points, so a factor of 16 square fewer grid points than the original, is a huge downsampling, we actually get quite good predictions of the turbulent flow.
Ricardo, how could you have it in a real setting? We work a lot with GANs, and we have a paper 2 years ago on physics informed GANs, but how could you actually have so many sensors? You're saying a few sensors, but 16 times less points than DNS is still 1 million sensors on 10 centimeters by 10 centimeters. So that's not possible.
Yes, that's a good question. So we're actually working with experimentalists on this. So our goal is to set up an experiment to test it in the next months. These people, what they do is the following. I mean, of course, these are, if you look at this panel here, I mean, there are still many sensors, that is true. But what they do is the following. They use thermography, so thermal cameras, to measure the heat flux at the wall. And the resolution that they have is something like this. Is maybe even finer than this, actually. And our architectures that we are developing now are based on predicting, based on the heat flux, the fluctuations. So because it's easier to measure the heat flux than to measure the wall shear stress components instantaneously. You can measure the instantaneous wall shear stress in 1 or 2 locations, as you say, but you cannot have so many sensors.
However, the infrared camera, I know these cameras because we use them at projects at the MIT. The infrared cameras, they don't measure heat flux, they measure the temperature. not flux, not gradients.
But with these guys, I mean, I'm not an expert in heat transfer, so I'm not really looking at experimental setup in detail, but they can measure the heat flux, actually. They measure the gradient of the temperature. I mean, of course, with the camera itself, you only measure the temperature, but they can measure the heat flux, resolved in time, and with a resolution in space that is, well,
I don't think it's possible to measure, just like it's not possible to measure stress directly, only with a model. The same thing, you cannot model, you know, all shear stress, they also always use a model. So I don't think there's a direct measurement on heat flux or there's a direct measurement on stresses.
I will check exactly what they do. For the wall shear stress, what they would use, I guess, I mean, is with hot films, you can measure the wall shear stress, but of course there is a model for the hot film, for the sensor that you are having.
Right, that's what I mean. Yeah, there's no direct measurement for stress.
Exactly. So I guess I understand your question. I mean, you don't measure it directly. Yes, you have a sensor from which you can infer that quantity. I mean, as the equivalent of the hot film for measuring the wall shear stress. But I see your point. I mean, you also have an uncertainty there that is associated to the evaluation of the model of that sensor. Yes, so it's not perfect at all. Yeah. Now I don't know exactly how they measure the heat flux, but I know they do it because we have. I mean, that's what we are doing for that setup. But I will look it up and share it with you also if you're interested. But I guess it's also some model based on the thermal measurements that one can estimate and the heat flux there. Yeah, and it's a good point about the resolution. So yes, I mean, if you have such a possibility of measuring on the whole plane, I mean, then this resolution is not so bad. I mean, it's a decent resolution comparable to that of the experiment. But I mean, this is of course ongoing work. But I was actually quite
Isn't
surprised.
this like an LES? I mean, if you do LES, you have you downsample 16 times, 8 to 16 times. So that's more like LES, going from LES to. I think that's more reasonable to claim. Yeah.
Yeah, that's true. And in these measurements that, I mean, with good PIVs, I mean, you get more resolution than, or similar to LES actually. So I mean, one is getting, and we also need to remember the Reynolds number. I mean, these Reynolds numbers are low. Of course, in the experiment, as you start to go a bit higher, then you cannot do it with this type of resolution. This is at Arita 180, and this is a low Reynolds number. So it's something that could be done in the experiment with current cameras and current technology, but yeah, and it's probably if one starts to go to reasonable Reynolds numbers, then this doesn't work like that. Yeah, it is true. But well, I mean, we need to push the experimentalists also to get better cameras as well. And this is about the super resolution part. But yes, I mean, just to say that from this, which is quite coarse, one gets a reasonable reconstruction of the reference field, basically. Okay, and then one last slide for this first overview of things that we do in my group. Two other applications. One is autoencoder-based non-linear model decompositions. This is also something with Hamidreza. So, I mean, basically, what we have with POD. I'm showing here for two obstacles, the turbulent flow between two obstacles, which by the way is also with NEC, and we have a complete database of different urban environments and different geometries and separations of obstacles. So that's also another set of data that we have. And then with different autoencoder-based approaches, Hamidreza, he can actually obtain these non-linear model decompositions with which 5 modes you can reconstruct 90 or 95% of the energy. An interesting approach is this beta variation autoencoder in which you can get orthogonal modes or almost orthogonal modes. So then one can also get interpretability there. So this is quite interesting work, which is about to be submitted very soon. So, and we think that autoencoders for model decomposition is also another area that is very promising. And then together with Jean Rabot in Oslo, we have several projects on deep reinforcement learning for control. So taking advantage of this non-intrusive sensing, then one can use this reinforcement learning to devise control strategies, not only in the context of turbulence. I mean, here I show his 2D cylinder, but also in the context of separation control, which of course, then you have larger scales, and it could be probably more suitable or more easier to use DRL to tackle that sort of phenomenon for separation control. So we're working both on turbulence control and on separation control in airfoils using reinforcement learning and simulations, basically. Okay, so I think that first part gives a bit of an overview of what we work with, and then I give the word to Hamidreza, so he will focus on the pins part.
Thank you very much, Ricardo, and thank you very much, everyone, for your attention up to this point. I will continue the discussion by talking about our recent work on physics-informed neural network and the usage of physics-informed neural network for solving Reynolds average Navier-Stokes equations. So this is the work that we have done in this research article, and you can find it online in arXiv. All the details that I'm going through is available in this article. So we have the Navier-Stokes equations for incompressible flows. So the continuity equation and momentum equations. This pressure is normalized with the constant density. So if we decompose the velocity and also pressure to mean values and the fluctuating parts, so this is the Reynolds decomposition, and impose it to the Navier-Stokes equations, we will obtain the Rand's equations. So all these fluctuating parts would be gathered in just one term called Reynolds stress tensor. And basically, we solve for the mean flow quantities. So using Rand's equations might be more applicable, of course, is more applicable for industrial applications because we don't need to resolve the turbulence. We just solve for the mean flow quantities. But the problem with the Rand's equations is that we don't have any particular governing equations or physical relation that describe these Reynolds stress terms. So can we go, sorry. Yeah. So basically, for solving these equations, we need some modeling assumptions to describe the Reynolds stress terms. So in this framework, these are the unknown terms in our physics, and we don't have governing equations describing these physics. So one choice is using linear eddy viscosity models, famous ones, and that describe a relationship between stress and strain rate. So this is the famous Pozinski assumption. And we can introduce the turbulent kinetic energy, turbulent eddy viscosity, and also this strain rate that described by the mean flow quantities, and use these parameters to describe the Reynolds stress terms. So there are a lot of turbulence models, zero equation models from Prandtl a long time ago, and one equation models, famous two equation models, such as K epsilon and K omega. So these models are very, very useful for industrial applications. Actually, they are good because we can apply them on very complex geometries, very huge simulations with a low computational cost. So these are useful actually, but there are some modeling assumptions in the framework that would reduce the accuracy of the simulations. So we choose an alternative way to solve the Rand's equations by knowing that we have some data, very small data set that described some of these terms. So this data set, we assume that we have some data for the physics, for the domain, and we have this underdetermined system of equation, and we are going to solve the Rand's equations basically without any specific model or assumption regarding turbulence. So we chose physics-informed neural networks as the framework. So we use spatial coordinates as the inputs and the mean flow quantities, including these Reynolds stress terms as the outputs. We are looking for a mapping from spatial coordinates to the mean flow quantities. And once we have these analytical relationship, we can use automatic differentiation to compute the derivatives. And once we have those, and we can construct the governing equations and compute the loss. So these residuals, actually, we can compute the residuals, and these residuals actually would be used to train the neural network. It assesses the limited data set to train the network, which is very, very good opportunity to use physics to train the network. So basically, our loss function would be comprises of these residuals, this loss function from the governing equations, and some loss from the boundary conditions. So we have the data on the domain boundaries here by red crosses, and inside the domain we have some points. We call it collocation points. And for these collocation points, we don't have the targets, and we want to actually obtain the solution on these points. So, these are the points that we are going to compute the residual of the governing equations on it. So these are unsupervised part of learning. And we have some data over the boundaries that would end up with the loss function based on the supervised learning, loss for the supervised learning. So these NAE is the number of collocation points, and NAB is the number of points on the domain boundaries. So this implementation of pins and this framework is very easy in TensorFlow. So TensorFlow provide us with this interesting gradient tape function that would do the automatic differentiation for us, and we can see that in few lines of code we can actually write a solver for Rand's equations, and this is very interesting that with a small code you can generate a solver that can solve a PDE. This is very interesting thing that pins would provide for us. So we use Atom Optimizer to start the training up to some point, and after that we use BFGS or limited memory BFGS to follow up the training and increase the accuracy of the solution. And we use full batch training for the neural network. We have a very simple neural network, fully connected, and 8 hidden layers. For each hidden layer, we have 20 neurons, and for all of them, we have hyperbolic tangent as the activation function. And also, we normalize the data to be more efficient for training. And so, for the first example, we solved the Faulkner scan boundary layer, which is a very interesting example for the laminar boundary layer flows with adverse pressure gradient or favorable pressure gradient. So basically, we are solving the 2D Navier-Stokes equations. This is an example to show the performance of pins for boundary layer flows, for laminar boundary layer flows. And this is, we choose Reynolds number of 100. This M would introduce the level of adverse or favorable pressure gradient that the flow has, and we can for this task, for this example, we choose a pressure gradient, adverse pressure gradient, which is high and near to separation, near to the beta value for separation. So if we solve this problem, and for solving this problem, we only use the velocity components on the domain boundaries. we don't use pressure. So we don't know anything about pressure. And we introduce L2 norm, relative L2 norm of errors as the error to measure the accuracy of the solution. And we can see that very excellent predictions can be obtained using pins. Actually, pins can solve the laminar 2D Navier-Stokes for this problem. And we can see that the error is very small, even for pressure. So this is very interesting. And with this, having these data, this gave us the idea to go for turbulent boundary layer and more complex flows. So we follow this a study with zero pressure gradient, turbulent boundary layer. The data we obtained from this article. So the computational domain, we have relatively large computational domain from Reynolds number based on momentum thickness from 1,000 to 7,000. And we evaluate the performance of the model, the accuracy of the solution for the local quantities and also integral quantities like shape factor and skin friction coefficient, and also inner scale quantities. So in this figure, you can see instantaneous flow that is very, very resolved. And this is the data that we average through the time to obtain the data for training. So our data set is obtained from the well-resolved large eddy simulations, averaged through the time to obtain the statistics, and those statistics we use for training, just for the boundary conditions. And we can see that very good predictions can be obtained even for this test case, which is turbulent, without any specific model or assumption.
Can you be a little more specific on what data you're using? You sort of skip the most important part, and how much of the data from LES are you using, and where are you using it inside the domain, only at the boundaries?
Only at the boundaries. Only at the boundaries we use,
What is the boundary? So this is the boundary here, right?
Exactly, yeah.
So you close this term, all these terms, just using boundary data.
Exactly.
Exactly.
All of the data, but only for the boundaries.
So you're able to. So that's an identifiable system. You're saying that I can have boundary data on these unresolved quantities for the closure, and use only boundary data, and that's
enough to guide the solution through the optimum point. You know, basically it's possible actually to use a small data to guide the optimizer with those losses from the governing equations to guide the solution to the optimal point. You know, it's actually the solution. It's not the solution is not unique, but it's accurate. So it's very interesting, I think, that we can just impose some data and then solve the underdetermined system of equation.
But it's an issue. I mean, you got lucky here. It's an issue of identifiability. I can easily break this. I'm with you, and I'm glad that things work. But I like to break things, so I can easily break it for you.
Yeah, it's actually, you know, if we increase the size of the domain, for example, this is the problem. Yeah, it's a problem. But if we be lucky actually to have some measurements, and it be a small and with some amount of gradient, so in that case we can guide the solution. Yeah, it's definitely true that it's a very ill-posed problem. So guiding the solution in that way might be tricky, but yeah, this work is just introduction that is possible to use some data.
Because we've done this for heat transfer problem where we don't have boundary conditions and so on, and you can have a few thermocouples that can give you that, but it's really a matter of if you try to generalize this, it's a matter of surface to volume information here. So you have here surface information that you convert to volume. And the question is, what is the threshold? For this case, it works. It seems to work well, right?
Exactly. We are actually for analyzing different things, adding noise to the boundary conditions, and also increasing the size of the domain to see the performance of the model. So it's a continuation of this work, and we are going to show where is the threshold for this type of simulations.
Text me when you break it, okay?
Sure.
I like things that break.
Sure.
Okay.
Yeah. And I'm going to follow with the other examples. So this one is the adverse pressure gradient, turbulent boundary layer. So we have beta. It's introduced the amount of adverse pressure gradient, and our domain and all these variables that we used for quantification of the results. So even in this case, we can obtain very good simulations for even Reynolds stress terms. So can we?
So Hamidreza, I just saw that there's a question in the chat that is relevant. Samuel Grauer, do you want to say it, Samuel, or should I read it?
I can ask it.
Yeah.
It looked like your boundary conditions are including Reynolds stress tensors. And so I was wondering if the solution is depending on the model that you use to calculate the Reynolds stress tensors for the boundary conditions, or is it independent of that?
Of course, it would be dependent because that data guide the solution to the actual solution. You know, they guide the framework to the solution. So the quality of the data is important. In this case, we used DNS data averaged through the time, or well-resolved LES, again, averaged through the time. So the statistics of those high-fidelity solutions, high-fidelity simulations.
What kind of, did you ever try not specifying a stress tensor at the boundary?
Yes, and the solution would not be good. You know, it would be not unique. The solution is not good. For some cases, we saw that maybe you can find for mean flow quantities for velocity good results, but actually it's not robust. You know.
Okay. Thanks.
Yeah, actually, the data is important in this framework. The quality of the data. So one thing is that adding noise to the data and then see the results, or the application would be for instance, if someone has some data over some boundary and measure with experimental data. You know, they have experimental data, and then one can learn these solutions, these continuous solutions from those data or not. These are questions that we are going to answer in near future. So yeah, with this example, adverse pressure gradient, we can see that again we can obtain very good solution even for the Reynolds stress term, less than 8% error. So it's very good. And also we can see that this shape factor, the nonlinear evolution of shape factor through the special evolution of the boundary layer, we can see that the model can predict this nonlinear evolution. So it's very interesting. And the other case is an airfoil, the boundary layer over an airfoil in this Reynolds number. We select just a small region on the turning edge of this airfoil from half of the chord to the end of the airfoil, and use the boundary data for training, and we want to find a continuous solution of the boundary layer flow in this case. So we can see in the next slide that all these all these Reynolds stress terms can be predicted accurately with a relative accuracy. And the mean flow velocity is very, very perfect. I think it's a good prediction of the mean flow velocity, streamwise velocity. So about 1.5% of error. And for the Reynolds stress term, it's about 11%. So I think it's good. Yeah, it's a very good prediction. And for the last test case, we solved the flow over the periodic hill, which is an interesting test case for turbulence modeling development and turbulence modeling. So we chose this domain from 1 to 5 based on the non-dimensionalized x with the height of the crest. So actually the data, the velocity in these on these boundaries, top and bottom, are 0. So only we need pressure for these top and bottom falls. And we only need 2 profiles of the data at the input and the output. And with those, we can train the neural network and then have a continuous solution in this domain. And we can nicely predict the evolution of this vortex and the reattachment point. And those are captured very nicely. We can see that the velocity profiles are captured very nicely. The error, for instance, for the streamwise velocity, the error is very low. For the wall normal direction is a bit high, but less than 20%. So it's relatively good if you compare it with other turbulence models for RAN simulation. And all these terms for the Reynolds stress are captured with a good accuracy. So through this work, we show that using pins, we can solve the underdetermined system of equations. It depends on the size of the domain and the quality of data, of course, but we can guide the solution to the optimal point. With knowing some data, we require a small data set. We use the data on the domain boundaries in this case, but it is possible to choose some sparse points inside the domain to train this neural network. And we saw that the computational cost is relatively comparable with the conventional RAN solvers. And also we saw that the performance of the model can be much better than the conventional solvers, conventional RAN solutions. So we think that it's very useful for industrial applications, and also when it's needed to augment the experimental data and have a continuous solution from sparse measurements, these kind of simulations could be very useful. Yeah, thank you very much. And with that, I'm going to give the floor back to Ricardo for the summary and conclusion.
And thank you very much, Hamidreza, for your part, and everybody for your attention. I will just leave the conclusions here. I mean, we have used CNNs and different types of deep learning approaches and the pins for different problems. So I'll leave it there, and you have also my contact information if you want to discuss more, or if you have questions or you want data, please feel free to contact. I saw a question in the chat about a Git. We have the article in a review process, so when it's published, we will make the Git open. But if you're interested in collaborating or you want to interact with us, I mean, I think there's no problem, Hamidreza, to share the repository and work together. I mean, we are very happy to collaborate and to share all the codes. But to make it fully open to the world, we will do it when if the article gets published, of course.
Okay, thank you very much. I got a question on the airfall plots that you showed a couple of slides ago.
Can you please introduce yourself, because there are lots of people from different places. Just say where you're from.
I'm Charlie Liu. I'm from Seattle. I'm a data scientist, actually, who had a background in CFD. I'm still interested in CFD. So, yeah, I think I must have missed the labeling on this one. what is solid and dash, and why are there different locations on the airfoil?
Yeah, exactly. It's a different
Oh.
location on the airfoil. These three white dashed lines are the different locations that we report the data. So the darker lines represent the points near the trailing edge.
Got it. Okay, all right. Great. Thank you very much.
Thank you for your question.
Yeah, thank you, Professor Vinuesa, for this great presentation, and also Hamidreza. And is there any other question for our speakers?
And really, yeah, I have a question for Hamidreza, since he's a user of pins. And you probably appreciate that every week we have lots of speakers over the years who they do pins, and they come here and they say how bad pins are and how creative they are, so they have improved pins. Now you seem to be happy with pins.
Exactly.
Can you say something about the limitations? So I'm interested in seeing what like the obstacles that you have, because we have an alphabet of pins by now. We have all sort of domain decomposition. So sort of I'm interested to see where could this be used in fluid application. So feel free to bash.
Actually, I think the framework is excellent, but the problem is the optimizer. If we find another optimizer that would give us some speed and some more accuracy, it would be excellent, even for Navier-Stokes equation, even for some simulations like DNS. So I think it's good to spend some time on the optimizer. The framework, I think it's very nice, because we can use automatic differentiation, and the differentiation actually is somehow analytical, so we don't need those errors for the domain decomposition and all those uncertainties, let's say. But we need definitely some better optimizers to move to the optimal point more accurately and with some speed.
Right. Well, that's the holy grail in machine learning.
Exactly. Yeah, exactly.
Okay, thanks for the feedback. Yeah, that's. But in terms of, you didn't talk about weighting, for example, your data versus the governing equations and so on. Did you use any weights, or it was just one-on-one? What did you do any tricks that you didn't tell us?
For this work, we just one-on-one. Yeah, for those terms. But yeah, it's a good way to combine the weights with the Adam optimizer actually, and it would speed up the process. So that was very interesting for me. Yeah, but yeah, for this case, actually, we use just one-on-one.
Okay, thank you.
Thank you very much.
Yeah, any other questions? Yeah, if not, then let's thank our speaker again for this great talk. Yeah, thank you very much, Professor Vinuesa and Mr. Eivazi, for your presentation.
Thank you very much for the invitation, and yeah, I mean, let's be in touch, and if we have more progress, we'll be happy to share it with you and to collaborate. And thank you for your feedback as well. Yeah, very nice. Thank you.
Yeah, thank you.
Thank you very much.
Yeah, so then now let's move on to our second speaker, Mr. Varun Kumar. So Mr. Varun Kumar is gonna start his doctoral research in Crunch Group at Brown University starting from January 2022. He is a mechanical engineer currently working as a systems engineer at Fujifilm Dymatics in Lebanon, New Hampshire. Varun completed his master's in mechanical engineering in 2016 from Clemson University. His research thesis was based on understanding the role and importance of design problems in creativity research. So today he will give a paper review where the title of the paper is PhyCRNet, physics-informed convolutional-recurrent network for solving spatiotemporal PDEs. So I think Varun, yeah, you can try share your screen now and start your presentation.
Sure. Thanks for the intro, Andrew, and hello, everyone. My name is Varun. Am I audible to everyone?
Yeah, we can hear you.
Okay, sure. Okay, can everyone see my screen?
Yeah, we can see it.
Okay. My name is Varun, and today I'll be talking about a paper that I reviewed recently. And this paper is called there's a new architecture that was introduced in this paper called PhyCRNet, which is basically a physics-informed convolutional recurrent network, mainly used for solving spatiotemporal PDEs. This work was done by researchers in the Northeastern University. And coincidentally, this work is somewhat similar to the topics in this work are somewhat similar to what Professor Ricardo talked about earlier in terms of use of convolution and recurrent networks. So here's a brief overview of the things that I'll be talking about today. So I'll be starting off with the key highlights and accomplishments in this work. Then I'll be talking about some of the research questions and objectives that motivated the researchers to look into PhyCRNet. I'll be briefly touching upon the problem statement that was used for this work. And then I'll be talking about the architecture for CRNet, the methodology that was used. And in this paper, researchers have actually presented numerical examples for 3 PDEs. And they have presented results for these 3 examples. So I'll be going over the results and some of the findings from this work. And in the end, they have the researchers actually have a small section where they discuss spins versus CRNets. So I thought it would be interesting to actually have that here in the presentation so that we can probably have a conversation about it. And the last 2 sections are basically some of the remarks and comments that I actually had on this paper personally. And the last topic would be what are the future research opportunities that stem from this work. So that's the basic structure for this presentation. So the key highlights for this from this work. So in this work, the researchers actually presented a novel physics-informed discrete learning strategy for solving PDEs. One of the most interesting aspects of this is this work was done without using any label data. So that was an interesting thing in this work. The authors also proposed an encoder-decoder convolution-recurrent scheme for low-dimensional feature learning. They also employ a hard encoding of initial and bounding conditions. And this thing is actually, the authors claim that this has a significant impact on increasing accuracy of the solution. And they have used a unique technique for this. At least it was unique to me when I read it the first time. But they have laid stress on this fact that using hard encoding actually gives them higher accuracy. They have incorporated an autoregressive and residual connection to simulate time matching. And they have also demonstrated excellent solution accuracy, extrapolability, and generalizability of the proposed methodology. So the research questions, and this is basically what motivated the researchers to actually look into creating a new architecture. So based on what I found in the paper, I think there are limited studies focused on using discrete learning to solve time-dependent PDEs without labeled data. And this was probably the biggest motivation for researchers, for the authors of this work, to actually look into PhyCRNet. There are some methods like ARDENS that exist for discrete learning, but it seems like they don't yield satisfactory results. And that is something that the authors pointed out in this work. So there were 3 key research objectives of this work. The first one was obviously to propose a new architecture based on convolution plus recurrent learning for solving spatiotemporal PDEs without labeled data. The second objective was also to propose a more efficient architecture based on CRNet and they call it the PhyCRNet S. And this is basically a lightweight version of the original architecture. And the third objective is to demonstrate the usefulness of hard encoding of conditions and result accuracy. Problem statement. So what the authors are trying to do is use this CRNet architecture to solve general multidimensional nonlinear coupled PDE equations, which have a form which is shown in this, shown here. And they have an initial condition and boundary condition that they use to train the network and get the output. The technique uses physical laws as constraints, and there's no use of labeled data, like we talked about earlier. CNNs are used here for faster convergence and accuracy, whereas RNNs are used for error propagation and the spatiotemporal evolution of the solution. One of the key aspects of this work is that this work is focused on rectangular physical domain with uniform discretization of physical and time space. And this is something that the authors have actually highlighted, that this method actually works only with uniform discretization. They have some suggestions as to how to improve it, but they do not actually show examples of it in this work. So this method focuses only on uniform discretization of space and time. So the basic methodology. I think most of us know that LSTMs are like potent tools for time series predictions, but it seems like training is difficult, especially for PD problems. And this was based on the work by Geneva and Zaberes. So in this particular work, authors have used a convolution in conjunction with LSTM, where the LSTM helps eliminate the vanishing gradient problem, which is like often present with RNNs. And this LSTM utilizes the LSTM construction in principle. The only difference being that it is taking input from a convolution network now. So that's why I think that they use the term convolution LSTM in this work. So this is basically a refresher where I'm showing like a basic structure of the LSTM. It has input gates, forget gate, internal cell and output gates, and based on the values that are being fed from the forget gate and input gate, the memory of the cell is updated. So the structure is same as LSTM, the regular LSTM. The only difference, like I said earlier, is that the inputs to these networks is being fed from a convolution network. And I'll talk about that in my later slides. Another interesting concept that I found in this work was the use of pixel shuffle. So this is basically where they have a convolution network where they're actually moving to low resolution feature maps. And then they have to actually bring them back to a higher resolution output. And that is where they're using this pixel shuffle in their architecture. So they are basically using an upscaling factor R, which they multiply to actually get higher resolution outputs. And the authors claim that this particular method is more efficient than deconvolution, which is generally required in when you use convolution networks. And it also introduces less checkerboard artifacts as compared to deconvolution. So this slide, this is where I'm showing the basic architecture of the CRNet. So we have 3 convolution layers, which actually transform the input, and they feed into the LSTM block. And from the LSTM block, they upsample the output, and this is where they're actually using the pixel shuffle methodology. And then they feed that back into a convolution layer where they are actually rescaling everything back to the required magnitude. And then the output is fed through an integrator. This is where they're actually adding the time step to this initial input and getting an output. And then like in general auto-regressive models, this output from the first time step is being fed as an input to the next step. And then that's how the whole architecture is designed. At the end of like all the time steps, the output that comes out is like used for differentiation, and this differentiation is basically using finite difference methods, and then it's being used to calculate the loss, and then retrain the network, and the whole process repeats again. And in this case, there is no batch normalization because there is no there is limited data. Yeah, basically the claim is that convolution LSTM, it operates on low dimensional features and provides higher accuracy and efficiency. So I'm going to pause there and see if anyone has any questions, because this is basically the crux of this work. So if anyone has any questions or comments, we can probably discuss that briefly.
I one comment is they say that having this residual structure makes it seem like an integration step, but then there's an LSTM layer as well, which kind of undoes that similarity. Did they address this at all?
I've not found details as to how they've addressed it, but that's a good question, and we can actually look more into it.
Excuse me. Hi, I also have a question. This is Panostinis from PNNL. So what I see here is that the output U1, U2, U capital T is a collection of values at the grid points, right? And then they use finite differences in order to compute the derivatives that will go into the residual, right?
Yes.
So all this thing depends on the accuracy of the finite difference scheme somehow.
Yep.
Right. So, I mean, I've seen work from this group before, and I always ask the same question, that somehow the good thing about neural networks, which is the ability to represent the solution of a PDE as a function of X, let's say if X is your spatial, is lost here. They treat the solution as an image. So they have they think of pixels as grid points, and then they have to resort to finite difference schemes. And that for me will create some issues with accuracy, for sure, in higher dimensions, even if you have a dense grid, which is very difficult to do in higher dimensions.
Yeah, I mean, I agree with you that using finite difference may be like a backstep as compared to where we are today. But it seems like they used it and they found good results.
Okay.
So
do they have results for more than one dimension?
They have like a 2D case.
Okay.
They have like a 2D, they have 3 examples in 2D dimensions.
Okay, all right, thank you.
I'll talk about the results in my later slides.
Thanks, thank you.
Okay, yep, nice question.
Hello, this is Lulu. So I have a question for the hidden layer. What's the dimension of the hidden layer here? Basically the RN layer, the dimension, H1, C1.
I have to look that up. I don't recall having that in the paper. I can look that up and respond to you. I'll have to look up the details on the work.
Okay, I see. So to clarify, so for example, for the U2, they have the for the second LCM, they have input H1, C1, and also the input from the convolution layer. Then yes, they do the pixel shuffle, right?
The pixel shuffle is being done in that upsample upsample part.
Oh, but then how do they combine the input from the C1, H1 and also the input from the convolution layer? Simply stack or?
Unfortunately, I don't have the details as to how this actually has been implemented. I only have like the structure in front of me. I don't have the code base to actually understand how this all is functioning.
Okay.
It will be published soon, but I don't have it right now.
Okay, thank you.
Okay, in case any people don't have any more questions, I'll probably move along. So this is in continuation of, this is just a continuation of the architecture that I talked about earlier, where this output from this first time step is actually being being calculated with the value of the time step, and then it's being fed to the next time step. The derivatives, like I talked about earlier, are being calculated using second and fourth order central difference approach. One of the difficulties with using this approach is that the derivatives cannot be calculated at the boundaries. And hence in this particular work, they have used like a padding mechanism, they call it, which I'll be talking about in the next slide. So one of the key ideas in this work, and one of the key propositions are made by the authors, is that they have used hard imposition of initial and bounding conditions. And this, and the authors have claimed that this actually helps them make accurate predictions. So how they have implemented this, there's not a whole lot of detail in this work. So I don't have enough information as to explain how this all works. But basically, they are incorporating the Dirichlet boundary conditions directly into the state variables via some sort of a padding operation. And for the Newman boundary condition, they're using some sort of a ghost cells, ghost nodes, with values of which are being approximated using finite difference. And the value of the padding changes during training. And in this case, they are working with periodic Dirichlet boundary conditions. So this is the lightweight version of PhyCRNet, and they call it PhyCRNet-S. So here they have used like a cycle index skipping encoder, which is this parameter T, I guess, which is like an empirical value, which can be obtained based on a trade-off between accuracy and efficiency. So what is
this is again. I have one question for the previous slide. For the previous slide, boundary condition. So this is classic in find difference, right? This is the classic way you find difference between codes. Then how can we say this is hard constraint? For example, the Newman boundary condition. If we have grid, it's never hard. It's approximately satisfied Newman boundary condition. It depends on grid size and so on, right?
Yeah. Yeah, I mean, they have not explained exactly how this has been implemented in this work. So unfortunately, I don't have a lot of details as to how they actually did this, and they don't have their code released yet. So I guess we'll have to wait until the code is available.
Okay, thank you.
Good question again. So yes, this efficient architecture basically uses this cycle skipping count, where in the original architecture, the output from the first time step is being fed to the next time step, and it goes through all the convolution layers and then goes back to the LSTM, and then it goes back through upsampling and that convolution. In this case, what they're proposing is that they don't do that auto-regressive step for each time step. Instead, they do that after a particular interval, and that is being determined by this factor tau or t. Instead of feeding the output from the first time step, they're actually feeding the output from the convolution LSTM layer, and that is being fed to the next LSTM layer. And the reason they can do this is because the weights are same, and it seems like the convolution layer that they have to convert input and feed that into the LSTM, that probably does not have an impact on the time-based evolution of the solution. It's only the LSTM that is actually handling the time-based evolution. And so that is the reason that they have given, is that even if you feed the next LSTM using the output from the first LSTM, it's still accurate and still going to be feasible to it. So I mean, as you can imagine, that with this architecture, you are probably going to have higher efficiency, because now your input data does not have to go through all these layers of convolution networks. But also, so your efficiency will be higher, but again, it will come at some cost in terms of accuracy. So there's always a trade-off between accuracy and efficiency, and that is where this factor T, that is where that empirical selection of this factor is being done. And they have like a table in the end where they are showing how this architecture compares with the original CRNet architecture. So they have three numerical examples in this work they have presented, where they're comparing the performance of CRNet against the PIN models, and the PIN model is based on the work by Dr. Eivazi, published in 2019. And they're comparing these two neural network architectures against a ground truth for all these three PDE systems, and the ground truth is being calculated using numerical methods. So the three systems that they are studying is like one of them. The first one is the Burgess equation. The second one is a lambda omega reaction diffusion system, and the third one is a Fitts-Nagumo-RD equation in 2D domain. Another thing that they have done in this particular work is that they have tested the generalization ability to different initial conditions for their CRNet architecture. So they have changed the initial condition, and then they have tried to verify if the model is still accurate or not. And another thing they have actually done is to actually perform a comparison between CRNet and CRNet-S, which is a lightweight version of CRNet. The setup for the study, they're using a spatial resolution of 128 by 128, and they're using a 32 gig NVIDIA GPU for this for training and testing the model. This slide, I'm basically showing all the other details of how many nodes they have used and what is the structure of their network. They're training their CRNet model for 10,000 epochs using an Adam optimizer. And these are just details of how the network is set up. What they're trying to do is basically compare PhyCRNet with pins, and then trying to compare both pins and CRNet against a ground truth. So they have also set up a pin model, which they are using to train and test on the three PDEs. In this case, they're using 4 fully connected layers, each with 80 nodes for the pin setup. And when I actually went back and looked at the original work, it had actually used 9 layers, each with 20 nodes. So there is some disparity between what they have used here and what was done in the original work. But I'm not sure if that is actually the reason for the results that we will see next. And they use like 10,000 epochs with the Adam optimizer and 100,000 epochs with the LBFGS optimizer for training their PIN model. And the metric they're using for calculating accuracy is given by this equation, where they are actually subtracting the output from the neural network from the field value that you get from the numerical approaches, which is basically the ground truth for them. So the first example they present is for like a 2D Burgess equation. The equation is basically used to define complex interaction of nonlinear convection diffusion with possible shock behavior. And the equation is represented by this. In this analysis, they have used a value of the value of nu is 0.005, and the size of domain is from 0 to 1. And the initial and periodic boundary conditions are generated from random Gaussian fields. And this is based on the work by Lee and authors. A time step value is like 2 milliseconds. And they have 1,000 time steps in the time domain of 0 to 2. So what they have done is basically they have trained the model from 0 to 2 seconds. And then they have tested the prediction capability of the model from 2 to 4 seconds. And the total empirical training time for this network was 24 hours, and they use a decaying learning rate. So this slide shows the results, and they are trying to compare the ground truth, which is basically the result from numerical calculations, and they're trying to compare it with their CRNet result from their CRNet. and comparing that against pins. So, and each column is showing like a time step. So the first column is showing like a time snap at t equal to 1 second. The second column under the training, the header training, the third column actually is showing a time step at t equal to 2 seconds. And they're trying to show extrapolation at t equal to 3 and t equal to 4 seconds as well. So as you can see, the ground truth and the output from PhyCRNet is actually pretty accurate in both the training and the extrapolation phase. And that seems to be consistent across this whole time domain that they are studying. Pins perform well during the testing phase, but during the extrapolation phase, pins start to lose out to PhyCRNet in terms of predicting capability. And yeah, I mean, you can see the errors for pins is higher as compared to PhyCRNet as you move into the extrapolation phase. So yeah, I mean, the basic conclusion from this particular example was that PhyCRNet produces accurate results with respect to the reference solution in both training and extrapolation phase. And based on this error graph that you see, you can see that the PhyCRNet is actually, there is no increase in the error propagation of PhyCRNet during the extrapolation phase, whereas pins actually start to have the magnitude of error for pins is actually higher during extrapolation, which might actually explain why the extrapolation or the testing phase actually shows more error for pin. And one of the reasons for this, as the authors have claimed, may be because of the soft bonding condition imposition in the pin.
What is extrapolation, Varun? What does extrapolation mean?
Extrapolation means basically the testing phase where you are using the train model and then you are looking for whether it can predict for the, from 2 to 4 seconds, there is no training, right? So you're trying to predict using the.
So you're freezing the weights. Are you freezing the weights at 2?
The weights are frozen. The model is trained. Now you're basically testing if it can predict the right values or not. It's the testing phase.
This is Dr. Abdul Khalik. Why do you have to extrapolate? I mean, why can't you use LSTM here?
That's a good question. I have to think about that.
We have experimented on different problems, and PINN goes very well with LSTM. And extrapolation is not a reliable process, or most of the time, you can say that.
So how you use the LSTM? Or maybe we should invite you to give a talk on this.
Oh, that's very kind of you. Yeah. Actually, we
give us in a nutshell. Yeah.
Yeah, we have experimented, and we are in that process now. That if you have a data and then you predict the parameters through PINN, and then you solve through PINN, and then after that, when you use LSTM, it will provide you very reliable results, then extrapolation.
Yeah, which they have it as part of their architecture.
We were using COVID data, in fact.
Yeah. But here's the PDE, right? You're doing ODE, right?
Yeah, that is ODE. But with the PDE, this kind of PDE, you can semi-discretize it, and that is a system of ODE. They're using just finite difference. And in rectangular domain. And PINN works, the whole idea of PINN is that you don't need a rectangular domain.
Yeah.
PINN works very well. And particularly when you are in the PDE and when you go the spatial direction, then you need data points in X direction. So that's what I was wondering, that we are at the advanced stage of writing it up, and we'll send you the copy that PINN works very reliably with this one, and particularly doing the time varying infection rates particularly.
Yeah, that's great. Yeah, I'd like to see that, and I will schedule a talk. But the whole thing here doesn't really make sense because pins are supposed to have the continuous training, right? It's not supposed to extrapolate. You just solve the so this it's a kind of odd use of pins. That's why I asked Varun, what does extrapolation mean here? They're not supposed to work actually, and so it really doesn't mean anything. But anyway, thanks for the comments, Haldi. I think that's great too that you do that.
Thank you.
Yeah, I'll have to read some more and try to understand what extrapolation means to them. So I can do that and send you a response.
Hi, Varun. This is Anirudh here. Also, I wanted to mention one thing. As I was playing around with pins, I saw one thing that if we add a bigger weight in front of the initial condition, the pin works good for extrapolation too, for up to certain extent. That's what I noticed when I was playing around with the pins.
Yeah, I mean, I'm sure there have been a lot more work done to improve pins. And one of the questions I had for the authors was, what if you use an advanced version of pins? Will it be better now? I mean, yeah, and even in this case, they're actually they're probably not using the complete potential of pins. They're training it to a certain, they're using a certain structure for pins, but they have not actually explored the whole gamut solution that pin may offer. So yeah, that was one of the comments I had for the authors was, what if you use a better version of pin? Will the results still be what we are seeing in this work? That's a nice idea, Anirudh. Thank you.
Thank you.
So the second example they present was using a lambda omega RD equation. And this is basically a multi-scale phenomena for chemical and biological process. And it simulates a turbulent behavior as well. And this is the representation for this set of equations. In this case, the reference solution is generated using spectral method in the space domain -10 to 10. And the PhyCRNet model is trained using 200 time steps in 0 to 5 seconds. And then testing is done in 5 to 10 seconds with a delta T of 0.025 25 milliseconds. The learning rate is decaying by 2% every 100 epochs. And that is a setup for their PhyCRNet model, the training part of it. So this slide is showing the results for this lambda omega equation. Again, we see the ground truth and the output from PhyCRNet is actually pretty accurate. And it seems to be performing well even during the extrapolation phase. Pins are accurate during training, but they start to lose out again in the extrapolation. And this is again, these are snapshots taken at 2.5, 5, 7.5, and 10 seconds from the output. So again, even in this case, we see that PhyCRNet seem to be outperforming pins at least in the extrapolation phase. In terms of error propagation, see that again, PhyCRNet seems to have better error propagation as compared to pins. And again, one of the comments that they had in the work was that pins show larger error at boundaries and do not extrapolate well. So that is something that they have pointed out in this work. The third set of examples they present is for a Fitts-Nagumo-RD equation. So these set of equations are used for portraying conduction of electrical impulses along a nerve fiber. And it's represented by the set of equation that you see here. So for this particular problem, the initial conditions were generated using random draws from Gaussian distribution. And the ground truth was generated using the fourth order time integration method. They use 750 time steps from 0 to 4.5 seconds with a delta T of 0.006. And then the result, and this was again extrapolated in the time domain from 4.5 to 9 seconds to test the model and its predicting capabilities. And in this case, also they have a decaying learning rate, which reduces by 0.005 every 50 epoch. So this slide shows again, the comparison between their results and pins as compared against the ground reality. Surprisingly, even with such a complex set of equations, they still have excellent predicting capabilities. I mean, the results are, you have to admire the results here because they are so accurate. It's hard to believe that such an accurate result can actually be obtained. But they have good results in training, testing, training and extrapolation for, and they're showing like time snaps from 2 seconds, 4 seconds, all the way up to 8 seconds. So the accuracy of the results is actually pretty outstanding. And again, pins in this case, pins have a hard time trying to even predict during the training phase. It seems it's probably because the system of equations is just so complex that pins are not able to replicate the actual results. So again, basic conclusion is that PhyCRNet performs well for predicting complex phenomena like the Nagu-Mord equation that we saw. And they are actually better than pins in terms of error propagation by 2 orders of magnitude. They have like some increase in error rate as they move to extrapolation phase with the PhyCRNet, but it seems like it's probably because of the complex set of equations that are used in this case. And they mentioned that this could be alleviated using longer time durations in training, but they don't have, they don't have examples of if that works or not. Moving on, they actually wanted to extrapolate and see if this PhyCRNet works when you have different initial conditions. Because one of the claims they have made in this work is that it's a generalization. This architecture is generalizable, and it can extend to different initial conditions as well. So in order to test that, they actually drew 4 different random initial conditions from a Gaussian distribution with a mean of 0 and a standard deviation of 0.1. And again, in this case, in order to show that this model is scalable and generalizable, they have actually extended the time duration for the study from 0 to 27 seconds for each of these initial conditions, and then compared the results to ground truth. The results here, this is comparing the ground truth against the results from PhyCRNet, and they're showing the results at time steps of 4 seconds, 8 seconds, 12 seconds, and 17 seconds. So they're showing the first row is like the ground truth for initial condition 1, and the results from PhyCRNet for initial condition 1 is shown in the second row. And again, you see extraordinary, ability to predict the actual ground reality. And this is actually the case as you move on to the other 2 bounding initial conditions as well. The results are very accurate and match the ground reality very well. In the last, they have like a study between, they have presented results of empirical study between PhyCRNet and PhyCRNet-S. PhyCRNet-S, as if you recall, is the lightweight version of PhyCRNet. And they claim that it's more efficient, although it comes, there might be some loss in accuracy when you use PhyCRNet-S, but they claim that this is more efficient. And they studied this for like the cycle, the skipping index. They studied it for 4 skipping index, 0, 10, 50, and 100 on the Burgess equation. They use the same training parameters for all 4 conditions. And the results were presented in this table where you see that overall, with increasing cycle index, which means the number of inputs to the next step, time step, being fed from the first time step, the number of times it happens is being lowered, which means that as you increase this parameter t, the accuracy of the model starts to reduce, but you start to see you start to get more efficiency from your model. There's one peculiar case where t equal to 10 seconds, where the PhyCRNet S actually outperformed PhyCRNet. And the reasons they gave were not very clear, but they seem to think that it has to do with the model being relaxed with the use of this particular value, and possibly reducing the overfitting because of the use of this value. But they don't have a concrete answer to as to why this is happening. In the end, they present a small summary where they have a discussion between PINS and PhyCRNet. PhyCRNet is basically a discrete approach, whereas PINS is a continuous neural network method. So one of the biggest advantage of PINS, like discussed earlier as well, is that PINS are mesh-free, whereas PhyCRNet rely on spatiotemporal mesh, which are limited to regular grids. But in order to overcome that limitation, the authors have proposed that geometric learning methods such as graph and neural networks can actually be used to extend to irregular mesh. But it seems like this is somewhat like a future research opportunity if someone wants to look into PhyCRNet and extend that to irregular mesh. PINS are both suited for global learning to capture the general dynamic patterns, whereas the discrete methods like PhyCRNet are more suitable to capture local morphology because of the use of CNN. So there was like one interesting idea that I had here was, could this be useful for modeling fracture? Because fracture involves sharp change in local morphology. So this might be useful to some people who are actually working in fractal modeling. That's just an idea. I'm not sure as to how it is going to perform, but that's just an idea. One of the biggest claims they make is that the use of hard encoding of the boundary condition helps them achieve better and more accurate results. And one of the things they have pointed out is that the use of soft boundary conditions that requires massive hypertuning of parameters. And in the case of PhyCRNet, because these are hard coded, the parameters of the network don't have to be, you don't have to spend a lot of effort in training the parameters. So that is another achievement or a key highlight of this work, that imposition of hard coded boundary condition is actually going to give you more accurate results. And they're trying to actually, they're a key proponent of that idea, I would say. So this slide is showing some of the remarks that I made on this work. One of the biggest things that I found that was, so they talk about this architecture being a generalizable architecture, but I think generalization is a broad concept. While they have presented some results which are motivating, and there is like definitely potential for this to become a more generalizable model for solving PDEs, but there are some other questions that have not been answered completely in this work. So some of the questions might be, what if we change the time of the space domain? Do we get the same results? Or what if we change some of the values that we use for the partial differential equations? Are the results still going to be valid? So in this case, they don't present any kind of sensitivity analysis, which I think might have bolstered their claim further. But I think that's something that was missing in this work. And the other comment I had was, it seems like one of the biggest limitations for PIDs is the soft imposition of the boundary condition into the loss evaluation. So if we manage to introduce a boundary condition, hard code the boundary conditions, what happens to the accuracy between PINs and PhyCRNet? So that was something that was a comment that I added for the authors.
Varun, this has long been resolved. The guy from Texas A&M, he showed the self-adaptive weights that we use now. That's not an issue at all.
Okay.
We used to do the bigger weights there, but the self-adaptive weights is trainable weight that has totally been solved. So they are comparing against 2016 when this pins version was developed.
Yeah, that was my guess because it seems like they were using a model which is probably not.
No, the boundary
latest
condition issue has been resolved. It's not. That's not an issue. So there. It's.
Okay, so I was not aware of that, but yeah, that's good to know. And future work opportunities. So this is basically my wishful thinking as to what can we use this particular architecture for, and how can we actually improve upon it. So I've recently started looking into Fourier transformations and what they can do with neural networks. So one of the ideas I had was whether Fourier transformation could be used instead of CNNs, whether that helps us improve the efficiency and accuracy for this particular architecture and other places as well. And the other idea that I had was, is it possible to have like a validation framework for verifying and validating these new methods that come out? Is it possible to have like a standard set of problems where you can use these new methods to see if they're actually valid or not? This is something that is maybe like a too far-fetched of an idea, depending on where the state of the research is today. But that is something that might be useful in the long run if someone wants to actually look into it. Some of the references that I had used in this presentation are listed down here. And that's, that's the end of my presentation. And if anyone has any questions or any comments, you can probably discuss them now.
Yeah, thank you, Varun, for your presentation. Any questions? Yeah, if not, then let's thank Varun again for this talk. All right, yeah, and thank everyone very much for the support during this period of time. And yeah, and then it's the end of the seminar this week, and hope that everyone have a good weekend. Yeah, bye.